Hey guys, welcome back to another lesson from the Apex Academy of Mathematics. We're learning the language of the universe begins here, and in today's video we're going to be looking at some circle geometry. We're specifically going to be focusing on applying the circle geometrical theorems to an actual question. We're going to be looking at what to think about, where to look, how to approach the question, and obviously to be more effective in working out problems like these. Now, these kind of questions usually have more reasoning than it has more calculation. Yes, you may have to do a little bit of adding, subtracting, maybe a bit of multiplying, but majority of your results will come from your ability to reason and calculate, whilst calculating, backing up your calculation with geometrical statements that you need to know. I've organized here about 5 or so questions coming from a variety of past papers from 2018 all the way up to 2021, and hopefully these questions from the past should give you a fair idea of what is it that you need to do and how you need to approach questions like these. Now, this topic is a very repetitive topic in the CXC syllabus, and so it keeps coming back because still there's not a lot of students who tends to really be effective at this question. So hopefully this video will be of some assistance to you. So without further ado, let's jump into the video. Be sure to smash the subscribe button below, turn on your post notification bell. If the video is of help to you, be sure to drop a like, and let's just jump into today's lesson. Alright guys, so we're looking at this year. We're looking at the year 2017. It's a January paper, and we're looking at this question here, question number 10. And it states here that the points P, Q, R, and S are 4 points on the circumference of the circle shown below. The angle QRS is 58 degrees. Now, what I encourage you as a student, whenever it is that you are doing an exam that involves circle geometry, one of the first things that you want to do is that you want to analyze the diagram. You want to give yourself clues before you dive into looking at the question that they're asking to find. So let's kind of peruse through the diagram here. The first clue that I see here is in the very first sentence given to us about the diagram. PQ, RS are 4 points on the circumference. Now that sentence there tells me that there is a quadrilateral that is inscribed inside the circle. And so this quadrilateral has its 4 points lying on the circumference. Now, in a circle, if a four-sided figure, if a quadrilateral is inscribed inside the circle, and its 4 vertex are lying on the circumference, then that shape is known as a cyclic quadrilateral. And so the property governing, or one of the property governing the cyclic quadrilateral, states that the opposite angle or the opposite angles in a cyclic quadrilateral, they are supplementary, which means that they add up to 180. So let's first identify the cyclic quadrilateral. The cyclic quadrilateral is created by the points S, R, Q, and P. So that is the shape that you're looking at. S, R, Q, and P. Alright? And so it means that this 58 degrees here and the angle down here sums to 180. So we know that for a fact. Alright? Another thing that I also see, and you ought to practice seeing this, is that usually when there's a center indicated on the circle, there's always a diameter or a radius or both. Now, when there is a radius or when there are radii inside the circle, it tends to form what is called an isosceles triangle. So the radius OS and the radius OQ forms a triangle with the chord SQ, and that triangle right there in the center is an isosceles triangle. Now, one of the property governing the isosceles triangle is that the angles at the base of the triangle are equal. They are equal, of equal measurement. So I know right away that if it is that I know what either of this angle is, if I know this one, I'll know this one. If I know this one, I'll know this one. And if I know both, or I know one, I should be able to find the one in the center by just doing some very basic geometrical calculations. Now, without further ado, let's jump into using what is it that we have already observed about the diagram to see if it is of any assistance in answering the question that is required. So we are asked here that we are to use geometrical properties of a circle to give reasons for each step of our answer. We are asked to find the angle SPQ, and this is also another concern that students tend to tell me that they have. They don't know how to identify the location of the angle. So the location of the angle is located at the letter that is in the middle of the three letters. So the angle is located at P here. And aha, as you can see, we are looking for an angle that is opposite to the 58 degrees that was initially given to us. So right there and then, I can safely say that angle SPQ is equal to 180 degrees minus 58 degrees. That sum, or that difference, is equal to 122 degrees. And so the reason for that is, as we stated earlier, opposite angles in a cyclic quad as quad, guys, are supplementary. That's the reason. So since the 58 degrees is actually looking at the angle, or it's facing the angle that we are required to find, then both of them will add up to 180 degrees. And that's basically the reasoning behind why or how we got the 122. All right, let's proceed into the next question. We're looking for the angle OQS. And again, you can see I've placed an arrow, a little indicator here to say that the angle is located at Q, which is right here. Okay, right there. So angle O cuts off the angle here at Q and heads towards S, is the one on the inside. That's the angle we're in search of. And again, you see, just by observation, we have already indicated that angle. We said something earlier about that angle. That angle is inside the triangle SOQ. And the triangle SOQ is isosceles. So we can start the process of, or start explaining the steps towards our answer by stating that, hey, triangle SOQ is isosceles, which indicates that the base angles are equal. All right, so we know that. Or we can just say radii of the same circles are equal, hence SOQ is an isosceles triangle. But what I also notice here, guys, all right, what I also notice here is that there is an angle that is at the center of the circle. There's an angle that is at the center of the circle. And that brings to mind another circle geometrical rule that states that the angle that is at the center of the circle that is created by a chord is exactly twice the angle that is at the circumference created by that same chord. Okay, so that's a little confusing. Let's give you some more clarity. Here is the chord SQ, and the chord SQ creates an angle at the center at O. But that very same chord SQ creates another angle. Zoom it up here, guys. It creates another angle at the circumference. Up there, that's 58. So what that means for us is that the angle that is exactly at the center, which is here at O, is exactly twice the size of the angle up there. So we can safely say that, let's go down here, guys. Angle SOQ is equal to 58 degrees times 2. And that's equal to 116. So this angle at the center here is 116 degrees. And so with that information now, we can clearly see that we are able to find either of these angles here, which we are interested in only this one. These two angles are equal, and they are in the triangle SOQ. So since we already stated that SOQ is an isosceles, which means an isosceles triangle, that's safe to say that we could say that angle OQS, which is the one that we wanted to find, is equal to 180 minus the 116 that we just found, and then all of that result now will be divided by 2. So 116 degrees taken from 180 degrees will leave us with 64, and if you divide the 64 by 2, we should get 32 degrees. And so the reasoning, we have already given a few reasons here, but the final reasoning here is that the angle at the center of the circle is, you can write out the whole word twice if you want to, it is twice the angle at the circumference, okay, subtended by the same chord. Okay, so you could write out all that fancy statement there, but we just want to make certain that we show at least a little bit of reasoning behind why we get, or how we got what we got. All right, pretty good. That was not a tough question at all, and that was just all that was asked of us on the 2017 paper. Let's proceed now to looking at another question. This question now is taken from, again, it's a May-June paper, 2021. That was just last year, a few months ago. All right, so let's see what other theorems now that we can pull out from this question. Again, guys, I encourage you to read the information up here, observe the diagram, see what clues you can find before you proceed into looking at what they're asking you to find. All right, sometimes identifying early clues will make it easier for you to write down the reasoning for your calculation. All right, so let's proceed into reading the instruction here. In the diagram below, EC, GF are points on the circumference. Aha, we just did a question like that talks about 4 points on the circumference. So even without reading any further, guys, right away you see that in this very first sentence here, we know that the shape ECGF is a cyclic quadrilateral, and we know this simply by the fact that they said that it is on the circumference. So CYCLIC quad. Let's identify the quad. Here it is, CGF, E. And what did we say earlier about angles facing each other in a cyclic? They sum to 180. So this angle plus this angle down here will sum to 180. And I know that this angle over here and this one over here will sum to 180. So we have some clues already. Let's use a different color ink here to identify more clues. Now, you see these two arrows here? They are already telling me that the line CD or the line CFD and the line AEB are parallel. Let's even read it to see if we could find it in here. It says here that EG is a diameter of a circle. And if it is that you have a diameter or a radius, there has to be an indicated center. So there is a center right there. Now, with that information, guys, we can safely say that if a diameter is drawn to touch a tangent, then I know right away that the angle created between the tangent and the chord is equal to 90 degrees. Because if a diameter is drawn towards a tangent, the angle created on both sides of the diameter is equal to 90 degrees. So zooming up here, right away, I can see that over here is going to be 90 degrees. And out of the 90, I already have 68. So in the event that I need to find this angle right in here, I'll know that I just need to take that 68 away from 90 to get that angle if it is required to be found. All right, so that's again the second line giving us more information, more clues. It says here that the tangent AEB and okay, so it says here the tangent AEB is parallel to CD. So I had already said it when I made the two circles around the arrow that they are parallel. Now, what does parallel lines do? Parallel lines create what is called corresponding angles. It creates what are called alternate angles, and it creates what are called co-interior angles. All right, it creates what are called co-interior angles. So it's going to be very, very good for us to know how to use those theorems in a few. All right. All right, so we have enough clues. We've read everything here. It says that the angle AEC is 68, which you can see all the way down here. AEC 68 and EFD is 106. EFD 106 degrees. Let's clear up our diagram here for a little bit more clarity. All right, so we have all those information. Let's have a look at what is it that they want us to find. It says here that we are to determine the value of each of the angles, show detailed working where necessary, and give reasons to support your answer. So the first thing here is to find the angle ECD. And again, guys, the angle is located at the letter that is in the middle. So let's touch the other two letters. E, here is E, that's E. Where is C? That's C up here. And D, ECD. So the angle is located here. That's the angle, ECD. Perfect. All right. So what can we do here? Aha. All right. So let's have a look now, guys. All right. Now, this is just what I saw at first, all right? So we're going to be using the tangent that they said that are parallel, okay? So this 106 degrees here and this angle down here, they are co-interior angles, all right? They are co-interior angles. So what does that mean? DFE, that's the 160 degrees. So angle DFE plus this angle down here, BEF, plus angle BEF is equal to 180 degrees. Simply because they are both co-interior angles. They are on the inside of the parallel lines CD and AEB. So this angle here is going to be equal to, so this is going to be 106 plus angle BEF, and that's going to be equal to 180 degrees. So angle BEF is equal to 180 degrees minus 106, and that is going to be equal to 74 degrees. All right, that's 74 degrees here. So why is it that I'm finding this angle down here when the question asks me to find this angle here? Now, there's a rule, or there's a tangent rule, that states that an angle that is created between a chord and a tangent is exactly equal to the angle created by that same chord at the circumference. Let's put some more clarity on that for you. So we're saying here that the angle created between the chord EF and the tangent EB, that angle is the angle we just found using this theorem here. So that's an angle that is created between the tangent and the chord. But notice now that the chord EF actually creates an angle. Okay. So it actually creates an angle here at the circumference at C, which is the angle that we want. So right away, without much more calculation, angle C, or angle ECF, or ECD, pardon me, ECD. So therefore, angle ECD is equal to 74 degrees, simply by the mere fact that the angle between the tangent and the chord are equal. That's the reason behind it. And this here is a Circl geometric theorem that you ought to know. All right? And that is the first way that I saw that I could have found that angle. Leave it in the comments, guys, if it is that you see another route in which you could find that angle. For the purposes of the video, I'm just going to be highlighting the method or the step that I see first, and I'll be sure to read your comments, guys, if it is that you see another way in which you could actually get that angle. All right? Perfect. All right, so let's proceed into looking at the other question here. Let's go on to the next page. Angle CEG. Angle CEG. Let's have a look at that, guys. CGE. So here is C, here is G, and it cuts off here down at E. So the angle is all the way up there. Okay? So how could we find that angle? Aha. So this CEG. Okay, so it's actually not CGE, guys, but it's CEG. Okay, so you see we have to be very careful. It says here CEG. So the angle is not at G, the angle is actually at E. So it's down here. So CEG, so it's actually here. And we said it earlier. We said earlier that this angle here is going to be equal to 90 degrees minus 68. And the reason why we said that, it is simply because the tangent GE, or not the tangent, pardon me, the diameter CGE meets the tangent AEB at exactly 90 degrees. And we already have 68 out of the 90. So it's easy to say that. Let's go over to the next page here. This angle is going to be equal to 90 degrees minus 68 degrees, which works out nicely to be equal to 22 degrees. And the reason behind that is a diameter drawn to a tangent is perpendicular. And the word perpendicular indicates to the reader or the marker that the angle is actually equal to 90 degrees. So that is why we took the 68 from the 90. All right, that's not a bad question at all. So that was pretty good. All right, and that we found that very easy simply because we had observed the diagram before. Final question for the final part for this question. CGF, okay, CGF. So let's see here. CGF, that's the angle up here. CGF. So let's insert this 22 here. All right. Very good. Now, CGF is quite easy to find. And again, when I use the word easy, it is relative based on how much of the circle geometry you know. Now notice that we found the 22 by taking the 68 away from 90 because the diameter CEGE meets the tangent AEB at 90. But notice that the diameter GE also meets the other half of the tangent EB also at 90. And out of that 90, we also have 74. So we could find this little piece in here. And when I find that angle, I'll tell you the reason why we found that. So now let's go over here and we can start our reasoning by saying that angle, let's name that angle that we're trying to find. That angle there that we're trying to find here is, let's say it is F, or say it's GEF, no problem. So angle GEF is equal to 90 degrees minus 74, and that's going to be equal to 16 degrees. All right, so let's insert that 16 degrees here. So if you put 16 degrees right in here, okay, we're going to give a reason for why we did what we just did. Yeah. So the reason for doing that again is because tangent, or I keep saying tangent, guys, diameter GE meets tangent AE, I believe it was AEF. Let's double check, guys. I believe it was AEF, AEB. So it meets the tangent AEB at 90 degrees. So that's the reason. That's the reason why we're able to take the 74 from 90, because the diameter GE meets the tangent AEB at 90 degrees. And then now with that, now let's go back to the main diagram again. We're gonna have to switch back and forth, guys. Notice now that the 22 degrees that we had found earlier plus the 16 gives us an angle here. So let's state the sum of those two angles. CEF. So angle CEF is equal to 22 plus 16, and that's equal to 38 degrees. All right, there's no reason for that. That's just clearly the sum of two adjacent angles. But then what's what's going to take us now to the mean angle? Why did we do all that just to find the angle CGF? Well, if you look carefully, that the angle CGF is opposite to the angle CEF, because they are facing each other. It's the angle at the top and the angle at the bottom here. They are facing each other in the cyclic quad, and the cyclic quad is CGFE. So we easily can say that angle CGF is 180 degrees minus the 38 we just found. So therefore we can say that angle CGF is equal to 180 degrees minus the 38 that we just found, and that's going to be equal to 142 degrees. And so the logical reason, or the geometrical reason behind that, is that opposite angles in a cyclic quad sums to 180, or if you can say they are supplementary. Alright? And that is the reasoning behind the calculation. So when you guys are doing circle theorem or circle geometry, guys, you have to be very familiar with your geometrical properties of shapes, geometrical angles, and just learning how to go elsewhere to get supporting information that will then therefore lead you to the primary question or the answer to the primary question. All right, leave me a comment in the comment section, guys, if it is that you are clear, if the explanation is clear, and if it is that you want as I said, more examples of this question. I'll be more than happy to work a few for you. Now, for the purpose of this video, I'm just going to be working one more, and I'm going to be creating a part 2 where I'm going to be doing 2 or 3 more questions highlighting the examples. All right, we're going to be getting this, guys. This is a topic that I want you guys to nail in the exam coming up very, very soon. So one final question here, guys, for this particular video. So this one is saying now the diagram below, not drawn to scale, shows a circle with center O. Aha! The points A, B, C, and M are on the circumference. So it seems as if, as I said here, guys, the previous 2 questions had this very, very same line here. So again, just looking at that with repetition, I will say that ABCM forms an cyclic quadrilateral. So ACMB, that is correct. AC, M, and B forms a cyclic. Okay, so right away what that tells me is that this angle plus this one down here sums to 180, and this one here and this one up here sums to 180. That I know for sure. Once again, guys, every time that there is a center, there usually is a diameter or a radius. And in this case, there is a diameter. There is also a tangent. If you observe carefully, that there is also a tangent here. And like the previous question, guys, when there is a tangent, if it is that a diameter or a radius is drawn to the tangent, then it forms a 90 degrees. Now, be careful. BC is not a tangent. BC is not a radius. BC is not a diameter. It's just a chord. Now, What forms the 90 degrees at the tangent is if a diameter or a chord is drawn to touch the point of tangency. If that doesn't happen, then there's no 90 degrees located at C. So just be careful if you might have misinterpreted what I said in the previous question. So let's just rule that out from now. We also see this 90 degrees here, so that could be helpful later on. Not sure. And we also remember that if it is that there is a tangent and there is a nearby chord, then the angle, let me just use a different color here for you guys. The angle created between the tangent okay, so remember now guys that the angle created between the tangent, the green line here, and the chord BC, the chord usually tends to create an angle at the circumference, and in this case it created an angle at the circumference down here. So this angle that you see here will be exactly equal to this angle here. Alright? So when it creates the angle, okay, so watch me again guys, the chord BC and the tangent CN creates an angle here. But the chord BC, it didn't create an angle at or up here, it created an angle just below. So this angle here and this angle here will be exactly the same. Alright? Alright. And this is just the observation process, guys. Okay? See, I haven't even looked at what they're asking me to find. I'm just locating clues that will make the process of learning or the process of getting to my answer easier. So I'm just going to be just clearing up the diagram a little bit here for you so we can get into the question. With those clues, let's see if we can get to our answers. So determine giving a reason for your answer. A, B, C. So see, they place the angle indicator here above B to say that the angle is located at B. Now guys, there are several angles at B here. There's an angle here at B. There's one here at B. And there's one on the, well, there's none on the outside. So there's two angles at B. So you've got which one you think you're finding. Okay? Let's touch the letter C where it gets cuts off. So ABC, here is A. Draw a line to B and cut it off at C. So the angle has to be the one over here. That's the one that we're looking for. The one there is another angle created at B. Alright, so we're looking for this angle here, guys. How can we find that? That's not difficult at all. Now, another theorem that you guys should be familiar with is the theorem that states that the diameter creates an angle of 90 degrees at the circumference. So here's my diameter, and if the diameter has two lines, pardon me guys, hold on. Okay, here we go. So the diameter has two lines leading from both ends here. One comes here and one comes here. Then the angle right here is. And we can support the fact that this angle is exactly 90 degrees by using the rule that says that the angle at the center of the circle, so there's an angle here at the center, it is exactly 180 degrees. The circle is twice the size of the angle at the circumference. So there's a line here that goes through the center that creates an angle of 180 degrees, but that line also creates an angle down at the bottom here that is half the size of the 180. So therefore, again, that's another reason why it's equal to 90 degrees. Okay, So it is 90 degrees here. So it's easy. We can safely say now, or before we state the correct answer, let's state how we got the 90. Angle ACB is equal to 90 degrees. Reason? You can say that the angle at the center of the circle is twice the angle at the circumference, but I prefer to say the diameter creates an angle of 90 degrees at the circumference. Okay, so that's a theorem that you all need to know. So the diameter creates an angle at 90 degrees at the circumference. Now with that statement, now we can say therefore angle, what is it that you're asking us to find? Angle ABC is equal to 180 minus the 2 we now know. They gave us 58 degrees and we just attained the 90 degrees, and so 180 minus, when we add 90 to 58 or 58 to 90, we're going to get 148 degrees. So if we subtract those two, we should get an of say 32 degrees here. Right? So the angle right here that you're asking us to find is 32 degrees. And what would be the geometrical reasoning for that? The sum of the angles in a triangle are supplementary. That's the geometrical reason for how we got the 32. Okay, so that's it, guys. That's it. That's how we got the 32 degrees there. Okay, let's go over to the next slide to see if there's more questions. There is. So angle CMB. Angle CMB, guys. So angle CMB, the angle here. Aha. So that angle now. It's nice. Alright, so what I have observed here is that we have a chord. We have a chord here. Let's identify the chord here. That's the chord CB. And there's also a tangent CN. So there's an angle created between the chord and the tangent, the chord CB and the tangent CN. But notice now that the chord CB created two angles. The chord CB created the angle 58 here, and the chord CB also created an angle down here. So 8 is actually equal to this 58 degrees here. Let's go back through that again, guys. Surely you want a repetition of that. Alright, so let's look carefully here, guys. Alright, we have a chord CB, and the chord CB creates an angle with the tangent CN. So this angle here is created. Now that very same chord that created the angle between the tangent and the chord itself creates an angle up here, which is equal to 58 degrees. So this angle right here is actually 58 degrees. Let's make a statement for that. So we're saying here that the angle CAB is equal to the angle BCN. Let's write that down. CAB, so angle CAB is equal to the angle C, I just forgot. Okay, so that's BCN, pardon me, that's BCN. Which is therefore then equal to 58 degrees. And the reason for us saying that is the angle at the, or the angle between, I should say, not at the, but the angle between okay, so the angle between the tangent and the chord is equal to the angle at the circumference. Okay, so that's the reason why we stated that angle CAB is equal to CN. Okay, and I've already demonstrated how we got the 58 and why they're equal, because the chord CB and CN creates an angle here, and the chord CB creates an angle up here, which is 58, so they are both equal. And so therefore this angle here is also 58 degrees, because the chord CB also creates the angle at M. So therefore BCN is also equal to the angle CMB, which is also equal to 58 degrees. And the same reason is as what we stated above. All right, so yeah, that's pretty much, that's it there. And finally guys, the angle NCM, all right, the angle NCM, so that's the angle NCM, that's the little piece in here, NCM. Well, here we have this secant here, NMB, it's a straight line. So the angle in here is equal to 180 degrees minus 58, and that's going to give us 122 degrees, because that's a straight line. So in here would be 122, and we already have the 90 degrees stated down here. So that little piece of angle that we're trying to find is going to be equal to 180 minus plus 90. Oh no, I think that something is wrong there. 122 plus 90 goes way past 180. So I think that something is wrong here. We're gonna figure this out, guys. We might have made an error. NCM, that's also a chord. Okay, sometimes you gotta take an extra look, guys. We will continue on this in part 2. All right, from here in part 2. All right, so I'm gonna have to close this video to get long. So I'll see you in the next session for the continuation. Do take care until next time. Please like, share, and subscribe if it is that you got some help here. Bye bye.